So having looked at an example with, of a state machine with D flip-flops, let us now look at the forward path analysis using JK flip-flops, because you might have to design an FSM either using D, JK, T, whatever flip-flop is available. Therefore, it's good to analyze do the forward analysis with all these three kinds of flip-flops so that we understand the working a little better. Okay, so I'm going to consider the following example. As usual, to remind you, in the forward path, we start with the circuit, we get the state equations, we get the state table, and then get the state transition diagram, right? So that's what we're going to do here. I basically have this is, a JK flip-flop. Okay, I have its true and complement. So in this case, I'm using only the true, so I'm not showing the complement output, right? This is J and K. Okay, my clock is here. Right? Uh, yeah. So what I'm going to do now is to determine J and K like this. So I have an AND gate here. Okay, and as usual, I'm going to call these outputs A and B. Right, and the input is and I have an XOR gate here. Right, which is being controlled by the input X. Okay, so this is my input X, and the other input to the XOR gate is coming from A. So this is going all the way up here and is being fed by the input A like this. So B is going there, and of course the clock is available here, right? So this is my flip-flop 1, flip-flop 2, right? So the first thing to do is to identify what is combinational block 1. This is combinational block 1. Okay, and let us put down the parameters for combinational block 1. Okay, it has number of inputs, I believe, right? If I am not mistaken, the number of states, number of inputs, and number of outputs. Okay, N, M, and K. Number of states is 2. Number of flip-flop outputs is 2. M equals 1 and K equals 0. Basically, there is no primary output, so there is no combinational block 2 in this particular example, which could also be the case, right? So having obtained the having seen the circuit, we can start off with the state equations. Right, so this output here is what I will call as a n plus 1, and okay, actually this cannot be this, because this is my j and k of the next state, right? So therefore I will just call it a and b, right, and then define what is my next state. Okay, so let us just we'll look at these things. So I'm going to call these outputs as U, V and W. Okay, so my state equations are basically going to say U is equal to simply it is going to be B times X bar, right, and V is going to be X bar, and W is going to be A times X, right. So no, W is going to be not A times X, sorry, it is A XOR X, right. This is A X bar plus A bar into X, right. And what happens, oh, I forgot the input to the J, this thing, yeah. So I have to also let me call this P, right. So P is just going to be B, okay. So I will say, if I look at the JK flip-flop inputs here, JA of n plus 1, right, is essentially my P, okay. So this is B, and KA of n plus 1, okay. The K input for which the flip-flops output is A, the n plus 1th state, okay, is going to be like I said, just, so this will be Bn, and this will be Bn times X bar. Likewise, Jb of n plus 1, okay, is going to be just X bar, right, and Kb of n plus 1, okay, is going to be XOR between A and X. So An X bar plus An bar times X, right. So this are Bx bar, and effectively this defines our state equation completely, okay. So let me take this over now so that I can use this to generate the state table next. Yeah, okay. So now, as usual, I am going to deal with my present state, okay, my input and next state, okay. So this is my next state, which basically is going to be An Bn. My input is obviously X, An plus 1, Bn plus 1, right. What what are the next states for this? And also now I need to worry about what is the flip-flop input, okay, because the flip-flop input is, it's not like a D flip-flop where whatever input you apply at D just comes out at the Q node, right. Depending on the combination of J and K, that is the characteristic table of the JK flip-flop, the next state will be determined based on that. So for example, So you also have to keep in mind the JK flip-flop, right? If I have a JK flip-flop in general, JK, and this is a flip-flop with a clock, right? The characteristic equation is Qn plus 1, 0 0 0 1 1 0 1 1, right? This is basically Qn, no change. This will set, okay, and this will reset, this will set, and this will toggle, okay. So you have to keep this in mind as well when you are generating this thing, right? So in fact, the next state an plus 1 and bn plus 1 can therefore be determined only through this characteristic table of the flip-flop that is being used. In the D flip-flop case, it was straightforward because that was just either you set or reset the output, right, depending on the input. In any case, so you start here, again go through all 8 combinations, 0 0 1 0 1 0 0 1 1 1 0 0 1 1, sorry, 1 0 1 1 1 0 1 1 1, okay. And let me just move this below here so that I get some space. I'm going to move this here so that I can go ahead and write the flip-flop inputs out here, right. So JA and KA, JB and KB, okay. So so using the state equation, we can use A and B and X and determine what this JA, KA, JB, KB should be fully, right, should be for each particular combination, and then we can use that in to determine what the next state is going to be, right. So I'll just move this down as well so that I get enough space. Yeah, okay. So therefore, if you look at JA, it is simply the flip-flop inputs are simply going to be Bn for JA, right. So therefore, it's very straightforward. I just take whatever Bn is, okay, that is 0 0 1 1 0 0 1 1, okay. So it is just this, that's all. There's nothing else that is being done here, okay. Now on the other hand, Ka is also going to be dependent on X, the input X. So wherever Bn is 1 and X bar is also 1, right. So I'm going to look at wherever Bn is 1, okay. So wherever Bn is 0, I can just write zeros, there is no problem. But wherever Bn is 1, I am going to look at where X is 0. So this is the thing, right, 1 0, right, and therefore I get 0 0 1 0 0 1 0 exactly. So this is how you do the analysis. JB is very straightforward, it is simply X bar. So it is just 1 0 1 0 1 0 1 0, okay. And finally KB is AN XOR X, right. So this one is AN XOR X. So it's very simple, you just take this column, and then XOR them and you put them here, okay. So this is going to be 0 1 0 and then 1, 1 0 will be 1 0 1 0, 0 1 0 1 1 0 1 0, right? So what we have done now is simply obtained what the next state of the flip-flop, what the J and K inputs of both these flip-flops should be, right? Now we have to resort to this characteristic table here. So we take each of these cases here, compare them against this table, and then figure out what the next state is going to be. Likewise, I will take this state, find out what the thing is, and then figure out what has to be the next state here, right? So therefore, JB and KB, right? So let's start with JA and KA. It is in 0 0, that means it will just hold the data, right? So that means AN plus 1 will be AN, right? So I am going to only look at AN plus 1 first. I am looking only at that flip-flop output, okay, which is flip-flop 1. I am going to look at only flip-flop 1, okay. Now JA and KA again are 0 0, that means it will just hold that state, AN plus 1 will be 0, right? And after that JA and KA are 1 1, that means AN will become AN plus 1, because you look at the characteristic table, for this input I am looking at this entry, it has to complement the input, right? And therefore it will just take AN and make it complement, right? Then JA and KA are 1 0, that means the output is going to get set, okay, 1 and 0, so the output will be set. Likewise, JA and KA again, the fourth entry, right? So if you look at, let me number them again, 1 2 3 4 5 6 7 8, right? So I am now looking at the fifth entry, JA and KA are 0 0, and which means that it will just hold that state as it is, right? Because so AN, whatever AN is, it will just continue to hold that for you here, right? Um, it will just hold that state for you. Then again JA and KA are 0 0 in the sixth entry, so whatever AN is, it will just hold it, right? Then your seventh entry JA and KA are 1 1, we are looking at this row here, 1 1 means it will just complement, so this 1 will become 0 here, right? And then we are talking about JA and KA being 1 0, and therefore it will simply set this particular thing, right? So therefore the next state for AN plus 1 will be 0 0, 4 1s and then 0 1, okay. Likewise, you got to do the same thing for JB and KB and BN plus 1 as well, okay. So what we'll do now is we'll take 1 0, okay, 1 0 here refers to this, that means the output will be set, okay, the output will be set, and therefore Bn plus 1 will be 1, right. Now then you come to the second entry, we are talking about 0 1, therefore that will be reset. Then we are talking about the third entry, which is 1 comma 0, and therefore you are again going to set, and then you are talking of 0 1, so you will again reset. Now 1 1 will therefore we are talking about this entry, 1 1 has to complement the current state. So here so when I am talking of JB and KB, I should be looking only at this column corresponding to JB comma KB, because it is going to affect only BN, which is flip-flop 2. I am now looking at flip-flop 2. Therefore, for the fifth entry, I have to look at this combination. I take BN, which is 0, and therefore I will make it a 1, okay. Then I come to the 6th entry, it is again 0 0 whatever Bn is, I will just retain. Then 1 1 again 7th entry, I am going to take this state and just complement it 0. Last one is 0 0 whatever this state is, I am going to just retain it like this. So 1 0 1 0 1 0 0 1, essentially this is the next state of the flip flop. So in this example we had to go through this additional characteristic table mapping, okay, because of this complex state characteristic behavior of a JK flip flop compared to a D flip flop, okay. So similar thing will be the case with a T flip flop as well, where you have to make sure that you are either storing the same data or retaining the state, or you're complementing the state, right, in a T flip flop. So that's something that you have to watch out for, okay. So therefore now I don't have to worry about this flip flop input case, because all I need is this particular state table. I don't care about anything else beyond this. With this I can generate my state transition diagram, okay. So I will now use this state table. Right, I will use this state table and then use it to generate the state diagram appropriately in this whole thing here, right. So what do I have? Again I have 2 flip flops and therefore I have 4 states that I have to worry about, okay. So like the last case, I am going to color code this X, okay. I don't have an output, so therefore I am not going to worry about that. So I have only AN and BN, right, and right, I am going to draw 4 states here: 0 0 0 1, okay, 1 0 1 1, okay. So starting from the state 0 0, right, which is row number 1 in the state table, if the input is 0, then you go to state 0 1, and the input here is 0, okay. Now if the state is 0 0 and the input is a 1, then you remain in state 0 0 with input equal to 1, okay. Now you come to state 0 1, and if the input is 0, you go to state 1 1. So that means you will go across like this with the input is 0, right, and 0 1, yes, okay. And then if on the 4th entry, if the current state is 0 1 and the input is 1, you go to 1 0 state. So therefore you will go like this, input is 1, right, and if it is at 1 0 and the input is 0, then you go to 1. You go to 1 1, and 1 0 and the input is a 1, then you go to the state, you remain in 1 0. Okay. Finally, you come to 1 1, and if the input is a 0, you come back. And if the state is a 1 1 1 and the input is a 1, then you remain in the state 1 1. Okay. So effectively, again using a JK flip flop, we have been able to come all the way from the circuit diagram through state equations, through the state table, using the characteristic table of the flip-flops, and eventually landed at the state diagram. Okay, so this should give us some more familiarity, right?